Morning. My name is Lee Moore, and I'm here with my colleague Aimee Sutton. And this session here, we're going to talk about RISC-V Design Verification. So I think the first thing is that there are a number of terms that tend to get bandied around with respect to verification, and you may have heard of some of these terms during the last 3 or 4 days, and what we intend to do is to try and elaborate on some of these and demystify them. I'm going to start off with looking into the design verification challenges for RISC-V. And to date, I think it's fair to say that most of the verification that's done is pretty much in-house. So if you look at companies like ARM or IBM, all of those verification techniques are done in-house. What we have with RISC-V is a challenge that verification now has to be done within our community, and this is what we've really been striving to work towards. We've been working with partners, customers, and also users of our technology. And currently there's no real industry standard, and that's what we're trying to move towards with the usage of verification IP, which I'm going to talk about during this presentation, and also by using some open standards which we're going to propose, something we call RISC-V Verification Interface. Now, before I get into a lot of detail on that, I want to do a little bit of a recap on some of the techniques that are currently used in terms of performing verification today. So the first one I'm going to talk about is something called post-simulation trace file compare. And post-simulation trace file compare relies upon a number of different components. So let me just go through these components individually. First of all, if we say there's a prerequisite as far as any of these approaches is concerned, which is that in order to execute code on either a target, whether it be a simulation target or a physical target, then you clearly have to have a tool chain in place. That tool chain has to be capable of targeting your particular target with the extensions that are supported on that target. And also, if you have things like custom instructions, then you're going to need support for those as well, whether they be done by the compiler or by inline assembler as part of the flow. The test programs themselves really fall into two categories, what we call directed tests and tests that are produced by instruction stream generators. Directed tests, typically you would write your own, and you can think of something as simple as a hello world program. Or it could be specific tests which are targeted at certain functional blocks within your design. There are also suites available, such as the compliance test group, and in fact there was a presentation, I think, just before this one in one of the other rooms. And these specifically target functional blocks within the certain ISAs. But then you also have commercial suites as well. On the instruction stream generator flow, what you really have there is the ability to configure a generator in order to target specific areas of functionality in your design. And what they will do is they will try to tease out certain aspects of the core, in addition to doing things like trying to exercise hazards, so read after write, write after write, that kind of thing. And there are open source solutions such as RISC-V DV, which I'm a little bit familiar with because I've used it as part of the Core 5 Verif implementation. But there are also commercial solutions as well, such as Valtrix Sting. So the instruction set simulator itself, we use this in order to execute the program that is being created using either directed or ISG generated ELF files. And the important thing is that when we execute this on the instruction set simulator, we want to get some information out of it. Now, that information has differing levels of complexity. So it could be as simple as just tracing the PC for the executed instructions. It could be including the disassembly of those instructions, or it could also have register changes for your general purpose, floating point, vector, and CSR registers. Also, what it may report to you are mode changes. So if you have a device which supports machine, supervisor, user, it may tell you when there are transitions between those different operating modes. And it also may give you information regarding exception and interrupt handling. Now, the same program needs to be run on the RTL for the device under test, and this would typically be done in something like System Verilog. But one of the most important things you need is that you need to be able to get information out in a similar form that you're getting from your ISS. And if you think about it, normally if you code up an implementation of a core, all it has to do is to execute the binary of the program in the correct fashion. It doesn't necessarily have to disassemble code or anything like that. So this is where we would have the requirement for something we call a tracer. And a tracer would effectively produce the output of the executed instructions and also provide information regarding register values so that we can do a comparison later on. The other thing I'll mention here as well is this thing we call RVVI trace, and I'll come back to it later on as well, but this is a way of taking that information from the tracer that's interpreting the execution of the program inside of the core and putting it into some standard format so you can have plugins into that tracer and can interpret those results as well. So if we stitch all of this together, what you have is a flow that looks like what you see on the diagram here, where you have the compilation of the program, either from an ISG or from a manually created file. You basically run two processes, one which is running the RTL, dumping out some information regarding the execution. The same L file then also runs on the ISS. It dumps out another log, and then you have to do a comparison. Now, one of the points you have to resolve here is that those log files may be in some different format, so you have to sort of massage them into some lowest common denominator of the two formats so that you can actually do those comparisons effectively. If we were to look at the kind of benefits that you get from this approach, that, you know, there's a lot of availability of generic simulators. We have the RISC-V OVP sim from us. You have Spike, you have Sail. On the downside, you know, as it says on the slide, you tend to have incompatible trace formats. So you're constantly manipulating files in order to get them into the same format that you can actually do the comparisons. And you also have to run this to the end, which sometimes can be a real problem for two reasons. The first reason is that if you have a very long-running simulation that you want to generate data for, sometimes the files can get huge, and I'm talking, you know, gigabytes and gigabytes of data that you need to generate and then compare. Also, if you have the execution of a program that gets into some lockup state, you're typically not going to detect that, and you could have a lot of wasted simulation cycles that you only can determine that you've got that once you do the comparison later on. Okay, let's move on to self-checking tests and signatures. So in this approach here with self-checking tests, typically what you do is you have a program, it produces a known result, and it could even be something that says, in the program, I'm going to add 2 to 3, I expect to get 5, and if I get 5, I'm going to print the message, test passed. Pretty simple stuff. And then on the signature comparison, in fact, signature comparison is something that's done as part of the ACT group, the architectural compliance. Similar to what I described before with the trace log, the main difference here is that what you're doing is you're capturing data at very specific points in the execution of the program. And what you do is you save those off to some signature file in memory and then dump out that data and you compare that data. Okay, so again, some of the pros and cons. Pretty easy to set this up, and also you have support from the RISC-V compliance suite, which is freely available. The main downside of this is that it doesn't have the sort of level of granularity that you do with some of the other approaches. So because you're only strobing data at very specific points, you may miss the interleaving of instructions as they execute up to those points. So let's take a look at step and compare. For step and compare, there are two important additions that we need here. One is the processor reference model, the other is the step and compare logic. Now, for the processor model, I haven't spoken much about this, but as you all know, RISC-V is highly configurable. You have quite a wide range of standard extensions as part of the definition of the processor. In addition to that, you have custom extensions as well. And so any model that you use as your reference has to be capable of being able to support all of those ISA standards that you intend to implement in your target, but also to be able to extend them for whatever are your custom extensions as well. This is key. In addition to that, you know, you really need the ability to control that model and to observe its internal state to be able to extract all of that data out for your comparisons. So this looks pretty similar to the one I showed before, which is doing the post comparison. The main difference is that this comparison is done at runtime. So the reference model is embedded into the single process that's executing along with the RTL. And then you have this control step and compare logic, which is actually doing the comparisons on an instruction retirement basis. It's ensuring that the state of the RTL and the state of the reference model are consistent in terms of the values of all of the registers. And then you can produce a result based upon that. The real benefit of this is that you don't get runaway simulations. Okay, you get immediate detection of any errors that occur in terms of differences between these two references. And also what you're able to do is if you have some debug capabilities, at the point where the failures occur, you can actually load up a debugger and then interrogate both of these references to see what the differences are due to. Now, up until now, we've only really been talking about synchronous execution of code, but one of the real big problems that we have is verifying the asynchronous inputs to a design. And this is something we've worked very hard to address. I'm going to talk a little bit about this. So in terms of the approach, what you require is the ability to drive asynchronous signals, so interrupts, debug, NMI, into your design, and to be able to have the design and the reference behave accordingly based upon whatever those asynchronous signals are. So this is effectively what it looks like. The front end is very similar to what we saw in the previous. The main difference is that there is also a route from the control step and compare to guide the reference model for handling those asynchronous events as well. But one of the benefits of this, of course, is you get all the benefits of step and compare, and you also get the response to your asynchronous events. The downside is this tends to be quite fragile because these are bespoke solutions to be able to pass this information. What they also tend to do is they also ignore a lot of the logic that is defined from the boundary of the device up to the introduction of those values into the instruction pipeline and all of the logic that resolves the introduction of the asynchronous event. So now I'm going to talk about verification IP using RVVI. So remember I mentioned RVVI earlier, which is the RISC-V verification interface. And these are some of the requirements, and these have sort of come out from the presentation I've already gone through today. So we need a reference model which is configurable, extensible. We need standard interfaces because we don't want to be able to manipulate data to get them into common formats. We want to start with a common format and use that in order to drive into our verification IP. And we want to be able to define methods to query that model, compare, scoreboard, and then report back when we see differences. Now, in addition to having the verification IP, what we have been working on with our partners, customers, and users of our technology is this thing we call the RISC-V verification interface. And I'll probably give a shout out here to three companies in particular, which is EM Micro, Scilabs, and Open Hardware, who have publicly been working on this with us. There are also many proprietary or commercial companies that have not announced that have also worked with us on this approach. But it consists of two main parts, this thing called RVVI Trace and the thing called RVVI API. RVVI Trace is effectively a container for data, and this allows you to take the information from the tracer of your RTL, populate the internals of it, such that you can have a plugin that connects to this and uses that data for the downstream tools, and I'll show that in a moment. And then in addition to that, for the RVVI API, these are the set of calls that can control your RISC-V verification IP. So the trace, as I mentioned, it defines information that's extracted from the tracer. It's built as a system Verilog interface. It supports the data in terms of the state, so your general purpose registers, CSRs, FPRs, vector registers, and it also handles your asynchronous signals as well in order to communicate those across. Also, the dimensions of this interface are such that it will support, if you have a device under test which is multi-hart, multi-issue, the interface can be dimensioned in order to support that as well. In fact, we have one customer who is developing a core using this technology, which is a multiple heart, 3-issue dual integer and one scalar execution unit. So it's a highly complex unit, but this fits in very well. And also the API, which I mentioned. So this is the second part of our VVI, which is the layer that allows the control and interrogation to that RISC-V verification IP. And for us, we have versions in both C and System Verilog that allows us to do this control. And it also, within it, it can also do the step and compare and the scoreboarding in terms of defining when differences occur between the RTL and also the reference model itself. So let's just go through what the components of the RISC-V IP actually is. So you'll see here from this diagram that we have, first of all, the ability to configure the reference model. Then you have to be able to do the synchronization. This is an important block so that when you do the execution, typically what's happening is you execute an instruction to retirement on the target, and then you do the same on the reference, and then you do your comparisons. An important feature of this flow as well is a bit of technology we've built called a prediction engine. I'm going to come back to that later on when I show a demonstration of this. But what the prediction engine does is it works to resolve when asynchronous events are pending inside of the core to determine where they are producing legal or illegal values, so that the report that comes across the interface from the RTL can be qualified as to whether it sits within that bounded set of possible outcomes. And then, as I mentioned earlier, we have the scoreboarding. We also have the pass and fail detection as part of this. Now, on those earlier slides there, I showed the fact that we drive this downstream tool using this trace to API, but also we have other plugins here as well, because it's also important to have things like coverage analysis and also logging. And so you'll see from this approach that we've built, you have other plugins that give you more and more information. If we put all of this together, so our test bench with our RTL, the tracer, and then connected through this Imperas DV interface, this is what you actually see. So this is a complete system whereby you can execute programs on your target RTL, and at the same time, the step-by-step instruction execution is being compared against the reference model that has been configured to determine what the supported extensions and behaviors are of that intended RTL. Now, what are the benefits here? Well, as before, I mentioned, you get your errors flagged immediately. It can find asynchronous and synchronous bugs. And I'm going to show a demonstration of an asynchronous bug, which is very difficult to detect normally. All the checking is done for you if you wish. And it's by having used the RVVI standard, it means that you can reuse it in other cores. In fact, for the open hardware cores, we've reused the RVVI interface on 3 of their E40 cores, so the E40P, X, and the S. So once it was implemented for one, it was basically reused in the other 2. Okay, we're going to get on to the demo. And the demo, I'm going to show 3 demos here. The first demo is very simple, which is going to show a typical working environment where a simulation will pass. And then I'll show a failing example where we have a synchronous error introduced, and then we'll go through an asynchronous event where we get a difference in the execution. Prior to that, I'll give it a bit of explanation so that you understand what's happening. So hopefully this is going to play a video here. So let's first look at the simplest case of constructing a test bench using the Open Hardware Core's E40X processor with an RVVI integration of the Imperas DV reference model. And in this example, we're just going to run a simple Hello World test case. And I've already got some scripts set up here. So we're going to run this guy. And you'll notice that this is using Xelium, and it's running the Imperas DV environment integrated into Xelium. We get a report from Imperas DV, and there are 3 sections to this report. The first section is effectively the prologue that tells us that it's loading a program to be executed and run with the RTL device under test. We have some output from the RTL simulation. So this is a Hello World program. It's just going to print this to the UART. But the most important bit is the report that comes out at the end that you see here. So in here, the Imperas DV verification report tells us how many instructions have been retired, the number of comparisons that have been performed. In fact, here we see we have a total comparison of just over 3 million. But the most important field is this one here, which is telling us it detected no mismatches between the RTL and the reference model for all of the state points that were compared. Well, that was hopefully that made sense. It was a bit quick, but you know that's a pretty simple test case we're running. But what I really wanted to show was what you tend to see when there's an error in the design, and that's what the next video shows. It's I should have mentioned actually that the code that's being executed here is the core for the E40X RTL. And so this is downloadable off GitHub actually. You can download it and play with it. But I'm just going to show it. Let's go back. I'm just going to show now introducing a design error into the RTL so you can see how it differs in terms of the report that's generated. Let's deliberately introduce an error into the RTL using the same mechanism as before. I've got it scripted up, and let's have a look at what gets reported by the IDV integration into Xilium. So as before, we have 3 phases, which are the execution of the program preceded by the prologue, and then we also have the epilogue. The important thing to note here is that we get a PC mismatch at one point in the execution. It tells us that the device under test and the reference are at different locations in the program. It also tells us that the instructions they're executing are different, which is expected, I think, and then also that when the instruction retires that we get different results in the register X9. What we really need to do is to look at the lead up to this event. So what we can do is enable some additional tracing, and this tracing is twofold. It includes tracing from the RVVI interface itself, and it includes tracing from the reference model. So here we see interleaved reports of retirement of instructions from both the RTL and the reference model. Here we see that the branch greater than equal unsigned is executed in both the DUT and the reference, but the subsequent instruction here, just before we get the mismatch, you'll notice that they both execute different instructions. Now, if this instruction for evaluating branch greater than equal unsigned is taken, it will go to instruction 19, the instruction at address 19B8. And what we see is that in the case of the RTL, that branch is not taken because it executes the next instruction, whereas in the case of the reference model, that branch is taken as it executes the instruction at the branch address. Now, as I mentioned, this is a deliberate bug that's introduced at this point. And we introduced it by use of a pragma in the RTL. So let's just search for what that pragma actually does. And let's search from the correct point here. So if we search inside the RTL, we can see that this is what's happening. So we have a comparator in the RTL code, which is used as part of the branch condition evaluation. And in this particular branch condition here, which is the greater than or equal unsigned, adding in this pragma will effectively comment that out, so the function gets removed. So now we can see why we get a divergence in our execution, because we have not effectively generated the correct condition code for the branch greater than or equal unsigned inside of the RTL. Hopefully that wasn't too difficult to follow. So what we've seen there are pretty simple examples of what we call synchronous DV. Now, the real complex type of DV that has to be undertaken is what we call asynchronous DV. An asynchronous DV is difficult because with an architectural model, which is effectively what our reference is, you cannot predict the timing that occurs between instruction retirements. But what you can do is you can look at all the possible outcomes of asynchronous events which would cause to happen. So imagine we're trying to show this illustratively, whereby we have this thing we call the staircase problem. And in this staircase problem, you have an instruction that has been retired, followed by a set of asynchronous events with increasing priority prior to another instruction being retired. But what you cannot predict is the latching behavior of those asynchronous events as they arrived from an architectural point. But what you can do is you can say, what are all of the legal outcomes? And you can use that as an envelope to say, these are the possible set of legal outcomes for these set of input events. And if the RTL produces something that doesn't fit within that envelope, then I'm going to flag that as an error. And in fact, this is quite a simple example that I'm going to show here, but we have some really complex examples in Core 5 DV where using the instruction stream generator, we would have situations such as a return from an exception would then have been preceded by another interrupt being asserted, and it was returning to an address of an instruction which had a debug breakpoint address placed upon it, and you also had an e-break instruction at that address. So all sorts of cascading potential asynchronous events. And so what's really important is to be able to evaluate all those legal scenarios that get produced and flag up whenever the RTL produces something that doesn't fit within that set. So this demonstration now is a little bit more complicated, but hopefully it will all make sense. And then we can, if there's any questions at the end, we can address them. Once again, we've deliberately introduced an error into the RTL in order to see what's reported by the Imperas DV reference model. The main difference here is that now we're going to evaluate some asynchronous events, and this particular test case is an interrupt test case where it generates a series of interrupts in different orders in order to ensure that they get evaluated correctly in terms of what is pending and the priority of those interrupts which are pending. So let's just run our script again. And you'll see here, this test is a little bit longer because it's a lot more comprehensive, and it's one of the standard tests actually as part of the Core 5 verification suite. So finally we get a report out telling us that we've had a number of compares and that we've had some mismatches. So what we really want to do is go back and look at the first mismatch that's reported in our log file here. And this is where we see it. The important thing to note here is that Imperas DV is telling us the reference model is unable to find a legal set of actions to converge. What this means is that it's looked at all the possible scenarios given the set of inputs, and it cannot find one that matches what the RTL says it's doing. If we look at this in a bit more detail down here, we can see what scenarios it has evaluated, and it tells us how it compares back to the RTL that's reporting. The first thing to note is that we've got a number of interrupts currently pending here, and we've also got a deassertion of the software interrupt. Now, because of the latencies on the processing of the interrupts, we can't know whether or not that deassertion has yet been processed by the RTL. So we have to consider everything that's pending and look at all the possible alternatives. So here we're evaluating one alternative that says, okay, what if it has been set to inactive, and here's one that says, what if it's still active at the point where it's being processed. The main thing to look at here is that between the device under test and the reference, that they've both ended up at different points in the vector table having taken a interrupt service routine. And in fact, the DUT is reporting that it's processing a machine software interrupt, whereas the reference is saying it's processing a machine external interrupt. So there's something not quite right here, that they both think that they should be processing different interrupts. Now, if we go back as before and take a look at our source code, so let's search for the bug that we introduced. So as before, we have a pragma. Let's search for that pragma. And this is what we see. Well, this block of code you're looking at is the interrupt controller. And within it, there is a block that evaluates the priority, as it says here. This encodes the priority order. And the highest priority pending interrupt which would be taken is the interrupt 31, which is defined as a custom IRQ. It's not one of the standard IRQs. Whereas the lower order bits in the pending register are things such as the timer interrupt, software interrupt, and external interrupt. So the highest priority out of these three would be external, software, and then timer interrupt. The bug we've introduced here has raised the priority of the machine software interrupt above the machine external interrupt here, which is IRQ11. So this is the bug we've introduced. So now let's just look at what Imperas DV told us again. So here we can see that the RTL, the device under test, took the pending interrupt, which was the software interrupt, which was incorrect. It was a lower priority. It also had a higher priority pending interrupt, which was the machine external interrupt. So straight away, we can see that even with these asynchronous events, we're able to predict what are the legal outcomes and then determine, did the RTL take one of the legal scenarios that we had predicted would be taken by the RTL. So hopefully that made some sense. It can be a bit overwhelming when you see this for the first time. For me, you know, I've been working on this for nearly 3 years, so I know it quite well. But this has been crucial in a lot of the verification we've been doing with designs where they need to ensure that the handling of the asynchronous events can be used as part of this flow, in order to make sure that the RTL is meeting the ISA specs. That's about it for my part of the presentation here. What I'm going to do, I'm going to hand you off to my colleague Amy, who's going to continue with this, and then we can take some questions at the end.
Thanks, Lee. Yeah, that was a great demonstration. Hopefully it cements the message that asynchronous event verification is a critical part of RISC-V processor DV, and it's a troubling problem for many people. So we hope that this helps you understand that there is a solution out there. All right. So now we're going to talk about some verification techniques which are popular in the ASIC and SoC world and can also be applied to RISC-V processor DV. We'll talk about verification planning, functional coverage, and assertions. Let's start with verification planning. So, why do you need a plan? Due to the nature of constrained random stimulus, functional verification could theoretically go on forever. A plan is needed to help guide that stimulus and establish a criteria for verification completion. So effectively, my verification effort is done when I have completed my plan. What goes into a verification plan is very important. Goals should be specific and measurable. For example, you might want to say a certain feature has been verified if a directed test targeting that feature passes, if certain functional coverage point is hit, or if a concurrent assertion succeeds. Another popular approach is metric-driven verification, or MDV. What this means is that your verification effort is guided by metrics that you track over time. The closer you are to achieving those metrics, the closer you are to achieving verification completeness or closure. Some commonly used metrics include code coverage, functional coverage, having all tests passing, and no new bugs discovered for a certain period of time. And to see some sample verification plans, you can visit the GitHub repository of the Open Hardware Group with the URL here on this slide. Now let's talk about functional coverage. Why do we need functional coverage? As mentioned previously, functional coverage is one method of expressing the goals for a verification effort and measuring that these goals have been achieved. It also enables you to measure the effectiveness of constrained random stimulus. So when you are writing an instruction stream generator, generating all sorts of random test programs, you need a way to know what you're testing. Many people write functional coverage code for their stimulus. It helps to know that you've tested a good spectrum of legal values and to know that you haven't inadvertently introduced a bias with your random constraints. So it's an industry standard best practice in the ASIC world, and in my opinion, it's a prerequisite for any comprehensive RISC-V DV effort. Especially when you're using randomly generated test programs, as I said, without functional coverage, you really don't know what you're testing. Now, let's talk about functional coverage in the context of RISC-V. You can divide RISC-V processor functionality into two broad categories. The first are standard ISA features, which is mainly instructions, their operands, and the values of the operands. So for example, you might want to collect coverage to know that every register has been used for each operand of the add instruction, let's say. This type of coverage is common to all RISC-V processors because it's defined in the specification. So the second type involves items that are specific to a particular core's implementation. Some examples of this are the behavior of interrupts, pipeline operation, or custom instructions. So for example, you might want to cover a set of legal configuration values for custom CSR. This category of functional coverage must be developed for this specific processor, and there's limited potential for reuse. So we're going to talk a bit more about the first category, which is functional coverage for the RISC-V ISA. Let's take a 64-bit RISC-V core as an example. This core could include several different extensions, and each of these has a number of instructions. If you were to implement all the extensions shown in this slide, you would have a total of 967 instructions. Since each instruction needs between 10 and 40 lines of system Verilog code to define the cover groups, we're looking at between 10 to 40,000 lines of code that need to be written. Keep in mind that this code doesn't have to be unique to a particular processor. This is coverage for the RISC-V ISA. And with that in mind, Imperas has developed a solution. It's a functional coverage code generator for the RISC-V ISA, which we call RISC-V ISA-COV. The inputs to the generator are a machine-readable definition of the ISA and a set of configuration parameters. So how it works is you would select the extensions that you want, and the generator will produce the functional coverage code for you. The inputs to the generator are a machine-readable definition of the ISA, and oh, I said that already, right? A set of configuration parameters. The generator produces functional coverage code in a modular way so that the coverage model can be built to match the extensions used by the particular processor. And during simulations, this coverage model is sampled using data from the RVVI trace interface, which my colleague Lee already described. And if you'd like to see some examples of functional coverage code, you can visit the RISC-V ISA-COV repository on GitHub. The code that you find here comes from the Imperas RISC-V ISA-COV generator. And you can also visit the Open Hardware Group's GitHub repository for some non-ISA coverage, so stuff that's specific to their cores, and it's open source. So you're welcome to take a look. All right, the next topic is another verification technique that's not specific to RISC-V. This is assertions. So assertions are rules that specify the correct behavior for some aspect of an RTL design. In the case of concurrent assertions, that behavior might occur over a number of clock cycles. System Verilog assertions is a language for expressing these rules describing behavior, and it's part of the System Verilog standard. But there are also other languages for assertions, such as PSL. This slide lists a few reasons why assertions are an asset to a RISC-V verification effort. One of these is to verify microarchitectural details that are not visible at the level of an architectural reference model. These rules can be written by core designers who have the detailed knowledge of the microarchitecture to be able to express the rules correctly. Another benefit of using assertions is that you can write cover properties to augment your functional coverage. This can help you measure the occurrence of low-level behaviors, and it can contribute to your verification plan. These rules can also be used in formal verification if you choose to use that method. Okay. Okay, now we've described a variety of techniques you can use for RISC-V processor verification. And we're going to leave you with some things to think about to help you choose the right technique for your project. So the first is considerations related to your specific processor or the device under test. The first consideration is the processor itself. Is it a new design? And this is very significant. If you're starting from scratch, you really can't assume that anything is working correctly. Are you extending a commercial IP core? If so, you should consider what you have changed and what areas your changes impact. You can also ask your IP vendor what they recommend for verification. Are you starting from open source? If so, try to find out how much verification has been done on that core and find out if there's any open source DV infrastructure associated with it that you can take advantage of. The goal of your project is another big consideration. Your choice of DV method will be very different if your silicon is a proof of concept, or if your core is a proof of concept, or if you're planning to take it to silicon. Finally, think about your need for reuse. Some verification techniques that my colleague Lee covered lend themselves better to reuse and will benefit future projects in addition to the current one. Now let's talk about some technology considerations that affect your choice of verification method. The first one is language. And you have a lot of choices today, and there's no right or wrong answer. The choice depends on many factors, including the preferences and experience of your team. Keep in mind that some techniques and methodologies are only available in certain languages. For example, functional coverage only exists in System Verilog, and UVM is only implemented in System Verilog and to some extent in Python. And since I mentioned it already, there's no conversation about verification that's complete without discussing UVM. Now, it's impossible to have a complete discussion about it in the time we have today, but I just want to highlight a few items for you to consider. So UVM is industry proven. There are many resources out there to help you make use of it, and there are some problems it solves really well. Some of these are coordinating stimulus among several interfaces, managing complex configurations, and controlling messaging. Conversely, it will limit your choice of simulation tools to those that support all the language features that it uses. And it's a heavyweight solution. The UVM library is big, and you build your environment on top of that library. You probably won't need or use all the features it has, and sometimes the UVM test bench gets complicated quickly. The last consideration here is, how do you create your processor DV environment? Do you build it yourself? Do you use open source, use verification IP, or maybe some combination of these? The important thing to realize is that each of those three that I mentioned comes with a cost, and you have to decide what you can afford and what suits your project schedule. The cost of building it yourself is time and human resources, and depending on the experience of your team, there's an unknown cost to making mistakes while learning. Similarly, using open source collateral will have a learning curve associated with it, and it will take time and effort to modify it to suit your project's requirements. Verification IP comes at a significant financial cost, but it will save you in terms of time and resources. And as I mentioned previously, it's possible that some of the techniques we discussed today can be combined in order to best suit the needs of the project and the schedule. There are many possible combinations, but here let's take the specific example of using both post-simulation trace compare, which is the first method that Lee described, and using verification IP. So you can potentially save money on VIP licenses by taking this approach, but it comes at the cost of having to build and maintain two separate verification environments. And that was the final slide of this presentation. Our friend here is smiling because he has figured out which techniques that he wants to use for his RISC-V verification project, and we hope you now feel better informed to do the same. Thanks for your attention, and Lee and I will be happy to answer any of your questions.
Hi. My question is regarding unit level testing, and where do you see the place of lower level testing in RISC-V core?
Do you want to take that one, Aimee?
It's up to you, Lee.
Okay. Well, so the only time I've been involved in unit level testing with what I've been working on, which is the sort of step and compare flow and using our technology as a reference, was a company who were developing it was the vector processor. They were developing a vector processor, and they used our technology in order to drive that vector processor in their RTL and use it as a reference to get the expected values back. But if we're talking traditional SoC approaches to block level testing, I don't know if you can comment on that.
Yeah, well, I think if that's what we're talking about, it makes sense to take a complex piece of logic, like Lee referred to the vector processor, and verify it in isolation. If possible, it's good to use a similar approach that you want to use for your entire processor so that you can make some reuse of maybe some stimulus drivers that you've written, you know, in order to stimulate that. Yeah, at least use the same language and the same general approach.
Any other questions? I guess that's it. So thanks very much for coming. Hopefully you've had a good conference. I'm tired, and I think we're about ready to go home. Thanks very much.
Thanks again.